I have adjusted my clock to this clock this morning, so it looks to me time to start. It's my pleasure to open this morning session, and the first speaker is John Friedlander from University of Toronto. The title of his talk is Selberg and the Sieve Positive Approach. So please.
Thanks very much, and thanks to the organizers for inviting me to this lovely conference. I'll start off, I was going to start off by thanking David Boyd for not being here to correct my mistakes, but let me start off instead by telling you that, well, if you're Jewish, you know what chutzpah is. If you're not Jewish, you might know anyway what chutzpah is. But if you happen not to know what it is, here's an example I heard long ago, many years ago. When my wife's brother came down to breakfast wearing my new silk bathrobe, I just thought he had a lot of nerve. But then when he smiled at me through my own false teeth, I knew he had chutzpah. Well, you can go to somebody's birthday conference and talk about something they haven't worked on. But when you go to somebody's birthday conference and spend the hour extolling the virtues of a third party, I don't know if that's a new example of chutzpah, but I'm pretty sure it's rarely used. Well, Selberg died last August, just a couple of months past his 90th birthday. And I'd like to talk about his contribution to Sieve Methods, which was one of his main interests. Even being 90 years old, he was not the very first to look at Sieve Methods, however. So we'll start with, as every talk on Sieve Methods has to, with some review for people in the audience who aren't as familiar with it as others. So Eratosthenes, around 250 BC in Alexandria, was the first to look at the problem of tabulating lists of primes starting with positive integers. So let's write down the integers from 1 to x, where x is 30 here. And we start by, how do I reach around here to 2, I guess. We start by looking at the first integer beyond 1, and that's 2, and crossing out all the multiples of 2. Then we go to the first uncrossed integer, 3, and cross out all the multiples of 3. When we do this, we notice that some numbers like 6 and 12 are getting crossed out twice. But we continue on. We go to the first uncrossed out number and cross out multiples of that. And now we find that not only do we have some numbers that are being crossed out a second time, like 10, we have numbers like 30 that are being crossed out a third time. Well, at this point, if we're using our heads, we stop, because we notice that all the numbers left here beyond the integer 1 are primes. And that's a simple consequence of the fact that if a positive integer is not a prime, it's divisible by a number less than its square root. And the square root of 30 is less than 7, which would be the next prime. Okay, well, Eratosthenes wasn't interested in counting primes as much as tabulating lists of them. But if we decided to count up what we'd done, we started with the integer part of x. I'm not a computer science, so I don't know this floor function. And we subtract out for every prime. P is always a prime unless it occurs in the middle of a word. We subtract out the primes up to for each prime up to square root x, we subtract out the multiples of p, there being integer part of x over p of those, and then we add in the ones we've crossed out twice. So that gives us this count over pairs of distinct primes less than root x, less than equal root x. And now for ones that have been crossed out 3 times, it was crossed out 3 times, then put back 3 times for 3 choose 2, so we need to cross it out again. And this reminds us of the Möbius function, which you all know, in this audience, you all know the definition. So if it's minus 1 to the r, or is that a nu? That's minus 1 to the r if n is the product of r distinct primes, and is 0 if it has a repeated prime factor. Nu of n will count the number of primes. Okay, so that's what we've counted up. And what we've come up with, if we define as usual pi of x to be the prime counting function up to x, we've come up with what is known as Legendre's formula, or at least a special case of it. We've recorded the primes up to x, other than those up to root x, and we also kept the integer 1, and that messy thing here is more compactly described using the Möbius function as follows. Okay, so what do? We want to estimate the number of primes up to x. Well, we're lucky. The number of primes up to root x is certainly less than the number of integers up to root x. And we're lucky because it turns out the number of primes up to x is much bigger than that. So this left side really is a good approximation to pi of x. Unfortunately, with the integer part function, about all we can do, hi Hugh, come on in, is replace the integer part of x over d by x over d. So that when we do that, we pull out the x and we make an error, we'll call the remainder, and that remainder is just what we get from the fractional parts because we've replaced the integer part of a real number by the real number itself. Okay, so at first glance, all we know about the fractional part of x is that, or is t, is that it's always less than 1, but that gives a horrible bound for the remainder term. This is much bigger than the main term, and actually it's possible using a little more thought to improve this. But the trouble is, this main term we've got, ever since Chebyshev, or let's say since Mertens, using some ideas of Chebyshev and some of his own, we know the asymptotic value for this. So that's not x over log x, which Gauss told us to expect, so we wouldn't argue. At least unless 2e to the minus gamma was 1. And 2e to the minus gamma, I think, occurred in an earlier talk. I forgot which one. It occurs a lot in Sieve Methods, but I'm pretty sure it's not 1. So the main term is wrong. And actually, it's only wrong, as far as we know, it's wrong because we know how to prove that pi of x is asymptotic to x over log x. Well, not till Brunn, I guess just about almost 100 years ago, Brunn made the first fundamental advances in sieve theory, and the way he started off in his first sieve, well, he gave up on the idea of getting an asymptotic formula. He decided he would be satisfied with upper and lower bounds. And it was pretty obvious from here that if we stopped after an odd number of prime factors, we had something too big and had to subtract something. And if we stopped after an even number, excuse me, I said it the wrong way around. If we stopped after an odd number, we had too little and had to add something. But if we stopped after an even number, we had too much and had to subtract something. So actually, that was the basic idea with which he started. And he also well, one way to cut this error term down is not to sieve by primes all the way up to root x, but just up to some smaller position. Well, if you sieve up to some smaller position and you get an upper bound, then that's certainly an upper bound for the number of primes up to x. If you sieve up to some smaller position and get a lower bound, well, it's not a lower bound for the number of primes up to x, but fortunately for us, it's a lower bound for something which has the same order of magnitude. That's true of the upper bound as well. Oops, I guess I should go in order. Okay, so if the only way we find out this much is by knowing the prime number theorem, why look at the sieve in the first place, other than so you can talk about something somebody else did at somebody else's birthday? Well, the value of the sieve is that it applies to much more general sequences than one can use the analytic method for. So let's generalize it. So we let A be a sequence of non-negative reals. We let P be a set of primes, and just for notational reason, we denote by capital P. So I guess that's not a prime, come to think of it. Capital P is the product of the primes in the set P going up to Z. And our goal is to figure out the contribution to this sum A sub m, coming just from those m which have no prime factor in which divides P of Z. So these parentheses stand for the greatest common divisor. And the basic property of the Möbius function is the starting point of all this, that it's sum to 1 at 1 and 0 for n bigger than 1 when you sum over the divisors of n. Another fact from the first month of elementary number theory is that the divisors of common divisors of two integers are just the divisors of the greatest common divisor. So we plug in this function, this sum that detects 1. We interchange the order of summation, and we come out with this sum, which is the more general form of the Legendre formula. And so we need information about this inner sum, AD. So it's the sum over the contribution to the sequence coming from the multiples of D. And what we assume is that ADX, this contribution, is a main term times a function of D plus a remainder term. And in our example, this is just what we did in our example. We replaced the number of multiples of D by a main term times a nice function of D plus something we hoped was small. In general, the main term looks a lot like the mass of the sequence. If I take this definition, A sub 1 is just the mass of the sequence. But it's just slightly different. Whoop, spitting, even with a microphone. So, for example, A sub 1 of x was the integer part of x. When x was 30, we were lucky, but if x is a real, then A sub 1 is the integer part of x, whereas the nice approximation, A of x is x. Okay, our function g, which we call a density function, it's always between 0 and 1. G of 1 is 1 because that's just counting the sum A1. We assume G is a multiplicative function, which means we assume that divisibility by two different primes p are independent events. And of course they aren't, especially when the primes are large, and that's the reason the sieve method fails to do what we want it to do. We certainly can assume the g's are less than 1, because if g of p equals 1, that means everything's divisible by the prime p, so why the hell are we looking for primes in here? The remainder term, as I said, is something we hope is small. Okay, there are a million examples where you can set up well-known problems and other interesting problems in terms of this terminology. Of course, that doesn't mean you solve the problem, as we all know. So here are just 3 quick basic examples. If we take A to be the characteristic function usually that's the characteristic function is, usually it's just the characteristic function of an interesting set, but I said it was a sequence of non-negative reals. So A is the characteristic function of these n's, and you might as well say n is even to start with, but you don't need to. In this case, g of p happens to be 2 over p if p is congruent to 1 mod 4 and 0 otherwise, and the remainder at p is less than or equal to. And we can certainly see that if we could sieve up to square root x in this example, and get something positive coming out, we'd prove there are infinitely many primes of the form n squared plus 1. Similarly, we can try and get twin primes by looking at products n times n minus 2, and if we could sieve up to the 4th root of x, then we'd get twin primes. Another way to try and get twin primes is just to start with a sequence of shifted primes, p minus 2, where p runs through primes. In this case, g of d is the Euler function, or the reciprocal of the Euler function phi of d, and the number of multiples a dx is connected with the number. It's just the number of primes up to x in the residue class 2 modulo d. And so the remainder term here will be connected with the error term in the prime number theorem for arithmetic progressions. Okay, and again, if we could sieve far enough, we'd get twin primes. Okay, now I want to go back again to Legendre's formula, which I'll repeat. So the first 2 lines are just repetition, but I just didn't want to have to, I knew I wouldn't find my old transparency when I was up here. And similarly, this is the basic formula for the Möbius function. And now our idea, or Brunn's idea, rather, is we're going to replace the Möbius function by sequences of functions, new sequences, lambda d plus and lambda d minus. And when we look at the summatory function of the lambda d plus, it's going to give us something which is bigger than this guy, bigger or equal this guy. And when we look at the summatory function of the lambda d minuses, that's going to give us something that's less than or equal this guy. And now if we go through the same manipulation exactly we went through here, at some place where we had an equal sign, we're going to have a less than or equal sign. And so what we get are upper and lower bounds for this thing we're trying to estimate. So we get an upper bound for what we want and a lower bound for what we want. And these guys look just the same as these guys did, except instead of the Möbius function, we have these new sequences, lambdas. Well, the main point of all this is we had a trouble with this remainder term, mu of d. And the reason we had trouble with it is it went on forever. The Möbius function is something that was given to us when we were born, although we didn't recognize it at the time. And it's just there. But when you invent your own sequences, you can say, okay, I don't want these sequences to live forever. I want them to stop at a certain point. And if they stop at a certain point, then this remainder term stops. It just stops. Okay, well, unlike the Möbius function that's one unique creature, well, are there any of these lambda d pluses and lambda d minuses? Maybe they don't exist. Well, actually there are, and there are tons of them. So how do we choose them? In the case of Brun, at least in the case of his first sieve, we choose them like this. If we want an upper bound, we go as we did before, and then we just stop after an even point. If we want a lower bound, we go as we did before, and then after the number of prime factors gets to this point, we stop. So that's just the same story over again. Okay, well, finally, I should say that I'm going to skip some history now. This was Brun's earliest sieve, and he went on and he worked on it and he refined it quite a bit and obtained quite a bit stronger results than this one did. This one was already strong enough to give some very nice applications. And then there was a school working on it, especially in the Soviet Union. And but we'll skip ahead anyway, because it is the 8th transparency, and eventually we should get to Selberg. So Selberg's first work on this was his upper bound sieve, which people sometimes call the lambda square sieve. The reason will become apparent very quickly. And Selberg was motivated to look at this sieve because of the work he'd been doing earlier on the Riemann zeta function. And it turned out that some innovations he used there, somewhat surprisingly, at least at first glance, turned out to be very useful for sieve methods as well. So let's start off. Let's take any sequence rho d, where d divides p of z, any sequence of reals supported on the divisors of this product of primes up to z. And we'll insist that rho 1 equals 1, and that rho d stops at a certain point. It might be the same z as here, or more generally, we could have it stop at a later point than z. And then for any n, we have the following inequality. This is Selberg's great mileage maker. Squares of real numbers are greater or equal 0. Rho of 1 is 1, so you get the top line, and rho are real, so you get the bottom line. Okay, so that means we can just plug this in where we plugged the lambda before. And this is automatically an upper bound sieve, no matter what the rows are. If I square this out and interchange the order of summation, it looks like this. That looks a little like the formula we had before, except we had something with a single sum over d. Actually, this is what we had before. And this doesn't look at instantly of the same form, but if you think about it a minute or less or more, you'll see that it is of that form if we write the lambda d plus as this sum where we group the pairs, the products of the pairs, whose least common multiple is d. This is the square brackets are least common multiple. And if this thing stops beyond z, or stops beyond w, then this thing certainly stops beyond z squared, or beyond w squared. And that's this d at which these coefficients stop, we're going to call the level of the sieve. Okay, now if I look at this guy here, if I look at it in this form, or in this form, and now I want to plug in my approximation, I guess in this form, I want to plug in my approximate formula for a sub x as a main term and a remainder term. And here's what the main term is going to look like. And now this is a quadratic form in these real numbers, rho d. And this is going to be an upper bound sieve. And we have an upper bound sieve, and this is the main term, so we want to minimize this quadratic form. And this can be solved. The way we can start out by is we can diagonalize this form. Maybe you can verify these things in your head. I can't, even though I've been seeing them for 40 years. We define the following function h of d. It's this product over these g's, over the primes of this rational function of the g's. And then we introduce new variables y in terms of the rows using this function. This is the Möbius function. I don't know if it looks like it. Yeah, sort of. Okay, and then applying not the first Möbius inversion formula you learned, but the second one, you can get the rows back in terms of the y's. And now, if you plug this in our quadratic form here, using this, diagonalizes to look like this. So these h's, because the g's are between 0 and 1, the h's are certainly positive. So this is a positive definite quadratic form in a certain number of variables, maybe a large number of variables, but it's a positive definite form, and it's got a constraint. You may forget what the constraint was. Rho 1 was equal to 1. Now we've got this in terms of the y's, and if we make the same substitution here, we get the following hyperplane. So the problem has become to minimize that quadratic form subject to that constraint. Now, Selberg had started studying university mathematics at the age of 12, so he certainly knew how to use Lagrange multipliers. There are other ways to do this, but that's the way he did. And the final result, using the normalizations he used, some people use slightly different substitutions to diagonalize this, but using the ones he used, it comes out with a very simple queued answer. If we let h be this sum, remember the d's are only going up to capital D, these are finite sums, then the minimum turns out to be h inverse, and each of the variables turn out to be h inverse. So that's a nice normalization he used. And if we plug back in to get the rows in terms of the y's, then we come up with this, which is no longer looking quite so simple. Okay, so now this sieve caused quite a stir when it was introduced in the late 40s, partly because Selberg was already on top of the world. A lot of the applications of the sieve still come from Brunn's sieve. You don't need Selberg's sieve, but there were a lot of new ones. So, for example, Brunn, not using the first sieve I described, but using somewhat more complicated, his later ones, which are really complicated in some sense, he gave the following bound for the number of primes in a short interval from x to x plus y. So you should think of y as maybe being, for example, root x, or something like that, or x to the 1/3. That's when it's most useful, this bound. And you get an upper bound of the right order of magnitude. Now, using Selberg's upper bound sieve, you could show that any c greater or equal to will do the trick. Now, Selberg, as he writes in some of his later papers, spent some time trying to improve this constant 2, because he knew it would have important other applications. The 2 is some sort of, in a sense, a natural boundary that if you can beat it, then you can do some wonderful other things. But actually, he was never able to do that. But thinking about this led him to one of his next themes in sieve theory, trying to decide what you could and couldn't do with the sieve. What were the limitations in general of what you could do with the sieve? And he found specific limitations, and he referred to this as the parity principle. So he constructed a number of important counterexamples which showed that there were certain things you could not do using the sieve axioms. And here are the simplest counterexamples. Suppose you take your set A to be not the integers up to x, but just those that have an even number of prime factors. So recall nu of n is the number of distinct prime factors. Well, if nu of n is always even in the sequence, then the sequence has no primes. That seems pretty self-evident. But it turns out that you can show that this sequence satisfies the basic sieve axioms that people had been using to the same extent, to the greatest possible extent, to the same extent that all the integers up to x satisfy. Now, there are things that the set of integers up to x satisfy that aren't satisfied by this set, but they weren't things that were being used in the sieve, not till about 30 years after this, 20 years after this. So that showed that you weren't going to produce primes just in a sequence from the sieve, just using these axioms. Well, you can just change this a little and take the set of all integers up to x, which have an odd number of prime factors. Well, if you stop and think about it, what you expect for such a sequence, this thing actually contains twice as many primes as you expect. I mean, it's half as many integers as the set of integers up to x, but it's got just as many primes as the set of integers up to x. So it's twice what it should. Well, there are many other more complicated examples. While Selberg was thinking about this, he came up with what he called a local sieve, which it's named that for a technical reason. No, it's not important why he called it a local sieve. Anyway, let's go to the von Mangold function. So this is the usual von Mangold function. You can generalize the von Mangold function in a very natural way to what I'll call what people call lambda 2 of n. And instead of living on the prime powers, lives on the integers with less than or equal 2 prime factors. And actually, the way I'll just tell you that one way of looking at this as a generalization is to say this is the convolution of the Dirichlet convolution of the Möbius function and the logarithm. This is the Dirichlet convolution of the Möbius function and the square of the logarithm. You now know what the generalization is. Okay, well, it's been known forever that the prime number theorem is equivalent to the fact that this sum is asymptotic to x, equivalent in the sense that either is easier to prove from the other than it is to prove from scratch. And Selberg showed the similar asymptotic formula, that's 2x log x if you can't read it, the similar asymptotic formula for this sum. But whereas this one is hard to prove, using elementary means at least, this one is fairly easy to prove. Analytically, this guy comes from a Dirichlet series with a simple pole. This guy comes from a Dirichlet series with a double pole. There are all sorts of reasons analytically where you can prove bad things don't happen twice. So that translates into an elementary proof of this. And from this, he was able to deduce elementary proofs of Dirichlet theorem and of the prime number theorem. And Erdős, as we know, also deduced proofs of the prime number theorem. Later, Bombieri generalized this and really turned it into a very beautiful part of the subject. That's maybe when Bombieri has his 70th birthday, I can talk on that. Yeah, right. When somebody else has their 55th birthday. That's very good, Greg, yeah. I don't need to wait for Enrico. Okay, so now we haven't talked at all about lower bounds, so let's move on. Now recall that the Brunn lower bound was very symmetric. The Brunn sieve was very symmetric between lower and upper bounds. In one case, you stopped after this guy. In the other case, you stopped after the next guy. Well, Selberg's was based on a square being greater or equal 0. There isn't any really natural analog of that for the lower bound sieve, but there is something very useful that came out of work of Buchstab in between the period that of Brunn and Selberg. Buchstab did a lot of work on the sieve, and one of the simplest of his discoveries is something that's a very, very basic part of sieve theory to this day. It's called a certain identity. What we do is we consider two different values of our z parameter, z1 less than z2, and consider the difference of the sifting functions. So this is just counting or summing the a's, say, counting the elements up which survive up to z1 but don't survive up to z2. And that means each of those is knocked out for the first time by a prime, which is between z1 and z2. And we are going to group those in accordance with the prime that knocks them out. Now, what we get for this difference is then a sum over the primes, grouping with the prime. Now, what do we get in the set knocked out by P? We get the set of things AM, where M is divisible by P, but no smaller prime. If we call the set for given P the set of AM that do that, then they're just the ones that are added up in here. These are the integers which are multiples of that P, and these are the ones, because of being the sifting function, they have no smaller prime than P. So we get the following formula. Now it turns out quite generally that this set AP satisfies in any reasonable example, if A has nice set of axioms that it satisfies, then this set AP does as well. Each of those do as well. So if we have an upper bound sieve for each of these, then because of this minus sign, we have a lower bound for this. Well, you say, yeah, but what about this guy? This guy's with a plus sign, so you need a lower bound for this. But Z1 is smaller than Z2. And if you are sieving only up to a little ways, then you can get something fairly accurate. For example, after the first step, you're just counting the odd integers. That you can do pretty well. After the first two steps, you're just counting the integers which aren't multiple of 6. You can do that. Which are prime to 6, I should say. So you can do that pretty well. So this, if Z1 is, it could be going to infinity, but not too quickly. This we can get pretty accurately. And if Selberg shows us how to get upper bounds for all of these, we get a lower bound for this. Okay, so that's the basic technique for using Selberg sieve to get lower bounds. Okay, so let's put together what we get out of these things. We've got the sifting function, and it's a main term, and depending on whether it's an upper or lower bound, and there's a remainder term, and we have the level we're going up to, and our d's live on the divisors of pz, and we construct the following diagram, where s is this parameter, log d over log z. Now, to explain what this diagram is telling us, what do we expect for this answer? What we expect probabilistically, heuristically, is when we knock out the multiples of p, we get 1 minus gp of them left. So if we do this for each p, this is what we expect our answer to be. And what we get for our answer is, for the upper bound, we don't get the expected thing. Instead of getting ax times this product, we get ax times this product times this fs, which is too big. It's bigger than what we want. And for the lower bound, we get ax times the product, the expected, but times this little f, which is less than what we want. So this is demonstrating how much we're missing the target. The target is this horizontal line at 1. And what this diagram is telling us, just from the existence of this function at all, where s is this parameter, is that we're going to get an upper bound of the right order as long as we can take d to be any fixed power of x, and we get a lower bound of the right order, not for the primes in our sequence, but for sifting up to some fixed power, and that will give us a set of almost primes. So if you find integers which are divisible by nothing less than x to the 1/3, then you've got integers with at most 2 prime factors, and so on. Okay, well, it's obvious from this formula that we want, well, it's obvious that we'd like d to be large because that makes s large. And when s is large, the upper bound and lower bound are closer to what we expect. Z, it's not so clear. It's clear we get a better answer when z is small because we get closer and closer to the expected answer. Well, that's what we were saying a few minutes ago in relation to Buchstab. If we don't sieve very far, we can do better. On the other hand, in this conclusion about almost primes, we do better, saying it has integers with no more than 2 prime factors is better than saying it has no integers with more than 100 prime factors. So in that sense, we do better if z is large. But for d, we want it to be as large as possible. Well, that's nonsense. There's got to be some constraint. The constraint is we've still got a remainder term, and we need it to be smaller than the main term. The size of the main term is the original thing we started with times some negative power of log x. For primes, it might be B might be 1. For twin primes, it's either 1 or 2 in our examples, depending on which one you look at. So the remainder, recall, looks something like this. And our goal is to get it somewhat smaller than this. So let's set it as a goal to get this for all a bigger than 0, although in practice often a equals 3 or a equals 5 or a equals 10 is good enough. And we can't expect to take d larger than x, but it turns out in practice that the lambda d's we've got, where's our remainder term? Here it is. We've got these RDs. In our examples, they were things like fractional part. They were sort of bounded by 1, almost. The lambda d's were the Mobius function, or imitations thereof. In practice, the lambda d's are bounded by 1, or something only slightly bigger. And hence, it's enough if we can do this. And so we're certainly not going to get d bigger than x, and probably not going to get d bigger than a of x usually either, at least once we've done this. Actually, since the 1970s, this step can be improved on, but until then, one just worked with bounds for remainder in this form. So an example of the newer results, now 30 years old, is the Ivanets theorem that there are infinitely many n such that n squared plus 1 has at most 2 prime factors. Okay, yeah. Yeah, the paper won't say it, but yeah. Well, not n squared minus 1. N squared minus 1 is true. It's called the twin prime problem. Yeah, any irreducible one. The same techniques work. Okay, so now I'd like to get back to Selberg, but what I need to do, I needed to introduce that, and I need to introduce a little more baggage that comes with the sieve, and that's the notion of sifting density. That's what Selberg calls it. Many people call it the dimension of the sieve. We had this density function, g of d, and our main term looked like the mass of the sequence times this sum. And remember, g of d in our examples, well, in all our examples, g of p was equal to a constant over p. And what we assume, we're going to assume that g satisfies the following asymptotic formula. That there's some constant kappa such that this sum has this asymptotic formula. And this is true in virtually all of the examples, all the important examples. And this constant is called the sieve dimension. In our case, in the 3-4 examples we looked at, it was always 1 over p or 2 over p, or in one case it was 1 over phi of p, so it was 1 over p minus 1. And this was all proved by Chebyshev long ago. So in the examples that held. Well, I'm writing a book on Sieve Methods, and my co-author and I spend a ridiculous amount of time arguing. We don't argue over mathematics, but over spelling of names, names for terms. We argue a lot, and I'm running out of time. And this is one of the arguments, and it's one of the less important ones, so I'm going to let him win. Without a fight. He'll win a lot of them even with a fight, I guess. Okay, so Selberg, as I said, was interested very much in the theory of the sieve, much more than anybody I know of. He really cared about the sieve just for its own sake. So here's an example of a theorem Selberg proved. It's quite a tough theorem to prove and will never be applied, probably. But it's rather general. We assume the remainder term has the form we want. And we assume that this is true for d equals x to the alpha for some alpha greater than 0, and that the sieve problem has some dimension kappa. And these are all extremely, they hold in virtually every example that you'd want to look at that this holds. And what he proved, that at least the sieve problem does have an answer. In other words, if you make these assumptions, then depending on alpha and kappa, of course, there exist optimal upper and lower bound sieves for this problem. You may not find them, but they at least exist. This is a tough theorem to prove. In the case where you assume the maximum you can about the remainder term, in other words, that it holds for every alpha less than 1, that's the best you could hope for. You can't approximate the number of multiples of a number bigger than anything in your set. If it does, then he actually exhibited what these optimal sieves look like. In the case alpha is less than 1, it's considerably more complicated. An important contribution Selberg made later on has to do with the sifting limit. I've reproduced this same picture we had a few slides ago, which had to do with our upper and lower bounds. Now, this point beta is called the sifting limit. It's a very important point because a lower bound of 0 is not much good to you when you're counting things that are non-negative. And here is where the lower bound starts to give you something. So that's a very important quantity, and it depends on the dimension, the kappa, that you have. One would like to know what the best what kappa the best, what beta the best sieve gives. If there is an optimal sieve, what is the beta which is it's gonna give? And it's known in the case where you have kappa equals 1, that's the most important case, that you can get 2. That was Selberg's upper bound for the primes in a short interval. That was 2. And you're not going to do any better. In the case where kappa equals a half, the half-dimensional sieve, that's a very important sieve for applications as well, you can go down to 1, which is the best you could hope to do, and you're not going to do better than that. On the other hand, there are a lot of problems, and problems where Selberg's sieve is really strong, where kappa is large and one doesn't have a clue what the best bound is. Well, one guessed that beta of kappa was 2 kappa. That's true. 2 points are on the graph, so let's say the graph's a straight line. That was nothing very close to the truth was known until Selberg actually, when we went to Selberg's 70th birthday party, he announced this result, and I'm really a little worried. Oh no, I can go a little longer. I think I have about 5.5 minutes, of course. And I started a minute late. Now, Selberg got a hold on the sieving limit, and he did it by introducing the following technique, which is just a refinement of what he had done in connection with his upper bound sieve, but in fact, he came up with this. He was 70 years old. So suppose we take 2 sequences, rho d prime and rho d double prime, and these are sequences supported in the usual fellows, and they both start off at 1, and we form this combination with them and call them lambda. Well, that should look familiar. In general, this is not a sieve. It's neither an upper bound sieve nor a lower bound sieve, but if we take the 2 equal, then we do get an upper bound sieve. That's exactly what we had before. That was Selberg's lambda squared sieve. So in that case, but in general you don't. But suppose these sequences rows were actually lambdas to begin with. Suppose they were actually either upper bound sieve or lower bound sieve. And now we combine them, but now we're assuming that we started off with sieves. Now, what happens, remember, theta denoted the sum of the lambdas over the divisors of n. If one can check that the theta for this guy is the product of the thetas for these two guys. It's not too hard to check. And what did we require about the thetas? We required that the first one be 1, and for an upper bound sieve, all the rest had to be non-negative. For a lower bound sieve, all the rest had to be non-positive. Well then, from this formula, you can read that if you started with 2 upper bound sieves, the next one's an upper bound sieve. If you started with 2 lower bound sieves, the next one's an upper bound sieve. But if you start with 1 of each, then you get a lower bound sieve. This is also a lot like how he got a lower bound from his upper bound. But now suppose you do the following. Suppose you take one of your sieves as the Selberg upper bound. Now it's a fact that the Selberg upper bound, as I said a few minutes ago, is really, really strong in the case of large kappa. Now, we're going to want a lower bound sieve. We're going to want a lower bound sieve. We're talking about the sieving limit. So we need a lower bound sieve for the other guy. Well, let's take a lower bound sieve that's really trivial. I mean, this is where you start off like Eratosthenes. You remove multiples of some primes, and then you just stop. Boom. Nothing. Well, this thing that you get by taking the product is then going to be a lower bound sieve. But the fact is, if you take D to be much larger than C, then all of the power of this sieve is going to come from this guy, not from this guy. And what you get as a result is you get a lower bound sieve which comes asymptotically close to the best possible sifting limit. Okay, I had one other thing I wanted to say, and I will do that horrible thing. I'll just flash it on the screen. I just want to mention the amazing results of Goldston, Pintz, and Yildirim, that they proved that if you look at the lim-inf of this quantity, the difference between the nth prime and its successor divided by the logarithm of that prime, that after a gazillion years, one knew it was bounded due to Chebyshev, less than or equal 1 by the prime number theorem, less than or equal a half by Bombieri and Davenport. After numerous papers in 50 years, bounded by a quarter, it's now 0. And I wanted to point this out because, as I said before, there are lots of things that you do with the sieve. Doesn't matter if you use Brunn sieve or Selberg sieve. There are lots of things where the combinatorial sieve that stems from Brunn sieve is stronger, but this one really essentially uses Selberg sieve in a very crucial way. And so I wanted to, you can tell I'm running 3-4 minutes longer than I thought, because I wanted to say just a few more words to excuse myself. As I said at the beginning, I should probably apologize, although I actually asked Peter's permission to give this talk. I've never asked anybody's permission to give a talk before, a topic, but I actually did. Now, so Selberg, Peter and I, to borrow Niels Brunn's words, to steal them actually, coupling our careers is sort of a near miss. We've always had interests that were sort of similar in some respects, but not overlapping, although God knows Peter has many more interests than I do. So as far as I know, Peter hasn't worked on the sieve. Selberg, as I mentioned, was 2 months past his 90th birthday when he died. Peter, you've got 35 more years. I set as a goal that when we all get together for your 90th birthday, I, who will only be 101, will attempt to give a lecture on your recent work on Sieve Methods. Thank you.
Yes, some time for some quick questions.
Near the end, John, you mentioned Selberg's result with the 2 plus little o 1 of kappa, and you said that that's essentially best possible. The fact that that's best
possible is not known, of course.
Okay, so
It's not known.
but
Okay, you're right. It's not known to be best possible.
okay, so that would still be
No, that's still open. They have lower bounds that are also a constant times kappa, but they're very far from.
do you
I know Selberg gave a lower bound also. I've forgotten what it was. It was something smaller. I think it beat the old results. I don't know if it's been beaten since.
okay, thank you.
Other questions? So we sang the